Section 11.9b, we're going into the differentiation and integration of power series. So when you look at the sum of a power series, you have a function f of x can be written as the series from n equals 0 to infinity of some constant times x minus a to the n. So we're representing our function as a power series. The domain is the interval of convergence. Because it only matters to us when it converges. The domain is the interval of convergence of the series. And we'd like to be able to differentiate and integrate these functions. And the following theorem says we can do so by integrating or differentiating each individual term in the series just like you would for a polynomial. This is called term-by-term integration and differentiation. Term-by-term integration and differentiation, just like you would for a polynomial. That's important for you to catch on. Guess we should have written differentiation first, but it's okay. So look at this theorem, and it says if the power series, like we stated above, has a radius of convergence of r greater than 0, then the function defined by f of x equals co plus c1 x minus a plus c2 x minus a squared plus all that equals the sum, the power series, just as we've stated above, is differentiable and therefore continuous on the interval. So look at the fact that when we take the derivative of this constant is 0. The derivative of this term is c1 times, and the derivative of x minus a is just the derivative of x, which is 1, so you get c1. Then you use chain rule here, and you have 2 times c2, so the derivative of c2 x minus a quantity squared would be 2c2 x minus a times the derivative of x, which is 1. So it's just 2c2 x minus a. So then we look at the next term, and it says c3 x minus a to the third. So the derivative would be 3c3 x minus a squared, and the derivative of x would be 1. So as you look at these, that's what the derivative is across here. So we could say that c sub n x minus a to the n would be n times c n x minus a to the n minus 1 times 1. So the power series, we can take the derivative of the power series to look like this using your chain rule. So if we take the derivative term by term, we end up with the series derivative, just as we talked about here. So let's make a note that if f of x equals can be written as the power series, n equals 0 to infinity, and we have c sub n, some constant, x minus a to the n, then f prime of x is the series from n equals 0 to infinity, n cn x minus a to the n minus 1, technically times 1. But you don't have to write that part, but that's where chain rule happens. So that's why it's there. Now let's go back and talk about the integration. If we integrate some constant here, let's start again. So if we integrate some constant here, we get CO times x minus a. And if we integrate C1 times x minus a, remember the x is your variable. So what you really have here is the integration of C1x minus C1a dx. So if you integrate that, you get 1/2 C1 x squared minus c1 a x plus some constant. Now you get that constant on all of them, so that's where that constant comes from. There is some constant at the end. So we can pull out the x here, and we have x parentheses, let's pull out a c1, x minus a. We can call it, we have a 1/2 here, so we can put it over the whole thing if we'd like. So that's where you get this term, c1 x minus a squared. And you could use u sub to check the rest. But what we find is if we were to take and integrate c sub n x minus a to the n dx, we let u equal x minus a, du equals dx. So we have the integration of cn u to the n du. So when we integrate that, we get u to the n plus 1, and then we have c sub n over n plus 1 plus some constant. So that's c sub n x minus a to the n plus 1 over n plus 1, and then it's plus c. So you can see that that's where this integration came from. We're going to have a plus c in there. So we can make a note here, and it says the if f of x equals the sum, the series from n equals 0 to infinity, c sub n x minus a to the n, then the integration of f of x dx equals the series from n equals 0 to infinity, c sub n over n plus 1 x minus a to the n plus 1. Now we would put a plus capital C out here real large, but those tend to get lost, so that's why they put it out front, so you don't lose that constant. And if we go back one slide, you can see the notes down here at the bottom. It says note 1. You can write it of that form, and we kind of already summarized them, so you've already got it. But the important thing to note is at the bottom of this theorem down here, it says the radii of convergence of the power series are both r. Because we had a radius up here, then the radius works the same for the derivative and for the integral. And that's what that note is making. Whatever your radius was before, it stays the same. Now, one thing to note here is your interval of convergence does not necessarily stay the same. It may stay the same, it may not. You have to check your new interval of convergence. One thing we need to fix here, let's go back and look. When you're looking at this screen, I want you to pay attention to here in the derivative, the bounds change from n equals 1 to infinity. And that has to do with the fact that it's the derivative and the constant, and those things come into play. So in this note here, let's change this to n equals 1. So make sure you've made that change, and over here, n equals 1. Okay, so let's look at an example, and we're going to look at the Bessel function, and it says j sub o of x equals the series from n equals 0 to infinity, and it's negative 1 x to the 2n over 2 to the 2n in factorial quantity squared. And we looked at this one earlier, but when you look at it, the only variable is right here. We have x to the 2n. Everything else is a constant. Oh, we have negative 1 to the n. I left that off. So when we take the derivative, we can say that the derivative of the Bessel function, and we take it term by term, so this becomes n equals 1 to infinity, negative 1 to the n. Let's look at all the constants. That's a constant. 2 to the 2n is a constant. N factorial squared is a constant. And then x to the 2n. So we multiply by 2n. So 2n, x to the 2n minus 1, take 1 away. So that's our derivative of the Bessel function. We take our derivative with respect to x. Let's look at another example. It says express 1 over 1 minus x squared as a power series by differentiating the equation that we start with. So as the derivative of 1 over 1 minus x. So let's think about 1 over 1 minus x. Those terms are 1, x, x squared, x to the third. Now remember this function doesn't equal each of those terms term by term. It equals the summation of those terms. It equals the series. So this equals the series from n equals 0 to infinity of x to the n. So when you take the derivative of this, the derivative of 1 is nothing. So that's why we back it up from n equals 1 to n equals 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x to the third is 3x squared, and so forth. And we know that the derivative of, we get 1 minus x quantity squared. So this equals the sum, n equals 1 to infinity. Now, if you take the derivative over here, you get n x to the n minus 1, which is correct. Now, if you'd like, we like the power series to be x to the n. So look at this. We could let's not say let's say replace, because in order to do this next thing, you have to actually think. So let's say replace n with n plus 1. So if we do that, we get 1 over 1 minus x squared equals the sum. Now, that means that n equals, when you let n plus 1, that means your bound was n equals 1, and now it's n plus 1 equals 1. So n equals 0. So we say n equals 0 to infinity, n plus 1, x to the n plus 1 minus 1, which cleans it up a little bit to be the series from 0 to infinity, n plus 1, x to the n. That's why we made the switch, was because we wanted to have x to the n there. So you can see how the two are related in this case. And the second answer looks more like a power series because it has x to the n. So the radius of convergence is the same as before. Up here, our radius of convergence was r equals 1. So down here, we still have a radius of r equals 1. Let's look at another example. Before we do, let's talk about this. Let's go back real quick. Let's talk about the derivative of 1 minus x. So think about 1 over 1 minus x. This can be written as 1 minus x to the minus 1, right? So the derivative with respect to x of 1 minus x to the minus 1 is negative 1 minus x to the minus 2 times negative 1, which is positive 1 minus x to the minus 2, which is 1 over 1 minus x quantity squared. That's why we took the derivative above, so you could see that it's true. Okay, so let's look at another example now. It says find a power series representation for natural log of 1 plus x and find its radius of convergence. So the derivative with respect to x of natural log of 1 plus x is 1 over 1 plus x times the derivative of the inside for chain rule is 1. So we get 1 over 1 plus x. Now 1 over 1 plus x can be written in power series form. So we're going to write it in this way, 1 minus negative x. So we know that this is 1 minus x plus x squared minus x to the third plus dot 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 when the absolute value of x is less than 1. We know that it's the power series. So since we know this is the derivative, if we integrate 1 over 1 plus x with respect to x, this gives us natural log of 1 plus x, because that is the antiderivative. Because your derivative of natural log is that, then your antiderivative of that is natural log. That's by definition of antiderivative. So what this really gives us is this equals the integration of the thing we have above, which is 1 minus x plus x squared minus x to the third plus ... dx. So if we integrate 1, we get x, minus if we integrate x, we get 1/2 x squared. If we integrate x squared, we get 1/3 x to the third. If we integrate x to the third, we get negative 1/4 x to the fourth, and so forth, plus some constant at the end. So if you look at that series is very similar to what we have before. What we have is we have x to some power divided by that number. You can see that happening there. Plus some constant at the end. But it's alternating, so let's throw in a negative 1. Negative 1 to the n minus 1, because the first term is positive. And we have the sum from n equals 1 to infinity. And then we have the absolute value of x is less than 1, because we know it's true if that's the case. So to find the value of c, we're going to put x equals 0 into the equation. So on the left-hand side, we have the natural log of 1 plus 0 equals, on the right-hand side, we have x equals 0, so that means that whole summation is 0 plus c. So on the left-hand side, we have natural log of 1 equals c, so c equals 0. So that means that this series from up above truly says n equals 1 to infinity, negative 1 to the n minus 1, x to the n over n, and then c is 0, so we don't have to say plus 0. We just say absolute value of x is less than 1. And then up at the top up here, our radius of convergence is 1. So down here, our radius of convergence is still 1. So the next example says, find a power series representation for f of x equals inverse tangent of x. Now, if you think about the inverse tangent of x, if you integrate 1 over 1 plus x squared dx, you get inverse tangent of x. That's the thing to note here. So by that term, this implies that if we take the derivative with respect to x of the inverse tangent of x, then we get 1 over 1 plus x squared. So let's say that inverse tangent of x equals the integration of 1 over 1 plus x squared dx. So that is the integration of, and if you think about it term by term, we have 1, well, let's write the power series in there so we can see it happening. Let's make a note down here. Let's say we have 1 over 1 plus x squared. This means we have 1 over 1 minus negative x squared. So this is the series from n equals 0 to infinity of the quantity negative x squared to the nth power. So this is the series from n equals 0 to infinity of negative 1 to the n and then x to the 2n. So that's our power series that we want to look at. Now, if we look at these terms, the terms here, I'm going to use this, let's rewrite it here, that the power series from 0 to infinity negative 1 to the n, x to the 2n. So when you put 0 in for n, you have a positive x to the 0 power, which is the number 1. When you put in 1, you have a negative x to the 2 times 1 is x squared, plus x to the 4th, minus x to the 6th, and so forth. Okay, so let's go back to this problem now that we can look at it more fully. And we say inverse tangent of x is equal to the integration of 1 over 1 plus x squared dx. And this equals the integration of term by term. It would be, we're going to integrate the terms that we have now listed above. So when we integrate, we get a constant. I put it at the front because we're ascending. Now the integration of 1 is x minus 1/3 x to the 3rd plus 1/5 x to the 5th minus 1/7 x to the 7th, and so forth. So now we're going to put, let x equal 0 to find c. So this means that inverse tangent of 0 equals c. The first term over here is c, plus 0, minus 0, plus 0, minus 0, plus, and so forth. Now the inverse tangent of 0 is 0. So at 0 radians is where the tangent is 0, and that equals c. That means that we can come back and write this problem and say the inverse tangent of x equals the integration of 1 over 1 plus x squared dx, which is, our constant is 0, so we can leave that off. X minus 1/3 x to the 3rd plus 1/5 x to the 5th minus 1/7 x to the 7th, and so forth. So now let's write that as a power series. So if you look at these terms over here, we can say inverse tangent of x equals, we have the sum of negative 1. Now if we start at 0, this is negative 1 to the nth power, because then it will be positive. And that's following what we have up above up here. Look at the fact that we have this. Now if we integrate this, negative 1 to the n is a constant, so it doesn't change. And x to the 2n should become x to the 2n plus 1 over 2n plus 1. So you can see how this integral here, how this power series is the integral of the power series above. So we have x to the 2n here, and when we integrate x to the 2n, we get x to the 2n plus 1 divided by the new power of 2n plus 1. Now up here, we have done this problem before, so we know that our radius of convergence is 1. If you look at this power series here, we have the geometric series where this r is negative x squared. So we know that the absolute value of negative x squared is less than 1, and that's what gives us our radius of 1. So since the radius is 1 up there, the radius is 1 down here. Just in case you'd like to see it done, you have negative x squared as your radius, which is less than 1. So that means the absolute value of x squared, the absolute value bars are not necessary, but they are less than 1. So if you have x squared is less than 1, you look at x equals plus and minus 1, polynomials. Now if you pick 0 for your x, that makes it true. If you pick 3 for your x, it makes it false. If you pick negative 3, it makes it false. So this says that this statement is true for these values when x is between 1 and negative 1. So that's what makes your radius 1 for the original, and you maintain your radius of convergence for the second one. And I think we might have time for one more. The problem says evaluate the integration of 1 over 1 plus x to the 7th dx as a power series. So that's the first part. And the second part is use that to approximate your integration. So let's start with this one. When we look at it as a power series, let's start with 1 over 1 plus x to the 7th. And we can write this as 1 as this form. Well, when you can write it as minus the negative 7th, that gives us this power series where we have negative x to the 7th raised to the nth power. Now notice this is geometric where r equals negative x to the 7th. So again, our radius of convergence is going to be positive and negative 1 like before. So we have the n equals 0 to infinity. This becomes negative 1 to the nth and x to the 7n. So if we list terms, I don't know that we need to. We've written it in this form. So if we integrate it term by term, we can say then the integration of 1 over 1 plus x to the 7th dx equals the integration of the power series, negative 1 to the n, x to the 7n, with respect to x. And this gives us some constant plus, we keep the power series, and negative 1 to the n is a constant, and we get x to the 7n plus 1 over 7n plus 1. We already know it's geometric, and so for our radius of convergence, we have the absolute value of negative x to the 7th is less than 1. So the absolute value of x to the 7th is less than 1. So, is less than 1. So x equals plus and minus 1. Again, you have a number line, negative 1 and 1. When you plug 0 into the equation, 0 to the 7th is less than 1. 3 is not. Negative 3 is not. So our interval of convergence we don't want the interval of convergence because we're talking about this rate. This comes from before you take the integral. So our radius of convergence is maintained. So here we get the radius of convergence is 1. So it's the radius of convergence for the answer. And it's the radius of convergence for the original power series up here. We know it's true up here for this original power series. That makes it true down here for the integral. Now the problem says to use our answer to integrate from 0 to 0.5, 1 over 1 plus x to the 7th dx, correct to within 10 to the negative 7. So we already know that if we integrate, we get c plus the sum from n equals 0 to infinity, negative 1 to the n, x to the 7n plus 1 over 7n plus 1. So if using the fundamental theorem of calculus, it doesn't really matter what c is because it's going to add and subtract out. But these terms are c plus x minus x to the 8th over 8 plus x to the 15th over 15 minus x to the 22nd over 22. And once we integrate this, we can do this from 0 to 0.5. So that means we end up with the constant is going to cancel out. So we get 1/2 minus 1 over 8 times 2 to the 8th plus 1 over 15 times 2 to the 15th minus 1 over 22 times 2 to the 22 and so forth. Now, if we use the alternating series estimation, we can stop. Well, we know over here this term is 1 over negative 1 to the n, 7n plus 1, 20 times 2 to the 7n plus 1. If we stop adding after n equals 3, it's better than after n equals 4. So that gives us 1/2. That means we're going to add these terms right here. And when we add the ones in the box, we get approximately 0.4995137.4. Thank you.